Everyone told you the chip shortage was over, but while the world looked away, a new crisis quietly ignited. In 2025, financial media outlets continuously cited a semiconductor glut, pointing to oversupplied consumer electronics, declining smartphone upgrade cycles, and inventory corrections across traditional PC markets. However, that superficial narrative completely missed the fundamental shift happening deep within the global technology supply chain. The traditional semiconductor cycle is officially broken. We are witnessing the rebirth of the global semiconductor deficit, but this time, the rules have changed entirely. It is no longer about a generic lack of silicon wafers or basic microcontrollers. It is about a total strangulation of advanced packaging capacity, specialized power management semiconductors, and energy, dense memory required to keep hyperscale AI clusters from overloading regional power grids. A massive chip deficit just returned, and you are likely looking at the wrong stocks. Silicon Photonics demand is quietly cannibalizing legacy production lines as we speak, while most investors are waiting for a dip in popular fabless stock tickers. A secret bottleneck in specialized packaging and lithography is already pricing the masses out. To profit in this environment, you must stop tracking chip designers alone and start tracking the lithography giants, power delivery component makers, and thermal infrastructure leaders who hold the keys to the entire hardware ecosystem. Welcome back to Earnings Per Page, where we save you hundreds of hours of technical research by distilling complex financial trends, industrial supply chains, and market dynamics into actionable masterclasses. Today, for video 51, we break down the hidden mechanics of the 2026 chip deficit, trace the invisible supply chain bottlenecks, and map out the strategic investor arbitrage opportunities hiding inside the AI infrastructure expansion. To understand why the global chip deficit has returned, we must first dismantle the optical illusion of the 2025 semiconductor glut. Surface-level market data looked comforting to first-level thinkers because consumer hardware demand normalized after post-pandemic spikes, leading to excess inventory in legacy 28nm and 40nm chips used in household appliances, basic automotive sensors, and budget personal computers. However, that legacy surplus masked an aggressive, hyper-concentrated demand shock originating from utility-scale artificial intelligence installations. Modern AI data center clusters do not function like traditional enterprise server farms that experience predictable peak and valley traffic patterns. They demand a continuous, unrelenting high-voltage baseline power load operating at maximum thermal output 24 hours a day, 7 days a week. This continuous load profile has exposed an immediate structural vulnerability. Aging electrical power grids cannot physically sustain the power draw requested by new multi-gigawatt computing facilities. Consequently, the bottleneck in AI expansion has pivoted away from basic GPU architecture towards specialized power management integrated circuits, high-efficiency voltage regulators, and high-voltage power distribution modules. These specialized power semiconductors, manufactured on specialized power-specific fab lines, are experiencing unprecedented lead-time expansions. Without these critical power-stepping components, a multi-billion-dollar array of advanced graphics processors cannot draw electricity from the regional grid without blowing out substation transformers. The oversupply in consumer silicon was a temporary mirage hiding a severe, localized deficit in the high-voltage infrastructure required to power 21st century compute. As data center operators push computing clusters to unprecedented densities, they have run directly into a hard thermodynamic ceiling known in hardware engineering as the thermal wall. Traditional server architectures rely on copper wiring to transmit electronic signals between processors, memory modules, and networking switches. However, as data transmission speeds push past gigabit scales into terabit territory, electrical resistance through copper traces generates catastrophic amounts of ambient heat while consuming an unsustainable percentage of total facility power just to push electrons through wire. In major urban compute hubs, data centers have become so thermally inefficient that municipal energy commissions are capping local power allocations, refusing to supply additional electrical capacity to facilities that waste gigawatts of energy on thermal dissipation. This physical wall has forced an emergency architectural transition towards silicon photonics. The integration of microscopic lasers and optical waveguides directly onto silicon substrates to transmit data using light rather than electrical current. By replacing resistive copper connections with light-based optical interconnects, data centers can achieve up to a 10-fold increase in bandwidth while reducing interconnect power consumption by over 70%. However, this pivot has unleashed a massive drain on global semiconductor fabrication capacity. Producing silicon photonics requires specialized lithography, ultra-precise etching, and advanced optical packaging tools, as foundry capacity is diverted toward optical transceivers and light engine substrates. Legacy production lines that previously manufactured smart grid sensors and regional electrical upgrade components are being cannibalized. The effort to solve the data center heat crisis is directly absorbing the manufacturing capacity needed to upgrade the broader civil electrical grid. Beyond power delivery and optical interconnects, the most critical physical bottleneck in modern artificial intelligence hardware is high bandwidth memory, specifically the transition to next generation HBM4 architecture. High bandwidth memory is created by vertically stacking multiple dynamic random access memory DRAM dies on top of an ultra-thin silicon interposer, connecting them with tens of thousands of microscopic through silicon vias. Because modern AI models require trillions of parameters to be accessed instantaneously, traditional off-chip memory chips create a fatal latency bottleneck. HBM4 solves this by placing energy-dense memory stacks directly adjacent to the main processor, operating within the same physical package. However, the transition to HBM4 has triggered a severe yield crisis across major memory manufacturers. Stacking 12 to 16 memory dies vertically with microscopic structural tolerances creates an extreme thermal and mechanical environment. During rigorous high-voltage stress testing, thermal expansion differences between stacked layers cause up to 40% of completed HBM4 units to fail, wasting months of high-precision fab time and destroying underlying silicon wafers. To make matters worse, producing HBM4 requires so much specialized manufacturing cleanroom space that memory makers are actively converting traditional DRAM production lines into high-bandwidth memory packaging centers. This conversion is cannibalizing the supply of standard memory chips used in industrial equipment, automotive systems, and consumer hardware, creating widespread price inflation across the broader memory ecosystem. Furthermore, efforts to simply build new factories to solve this issue are stalling because local energy commissions are withholding power permits for new energy-intensive fabs. Faced with severe power limits and thermal bottlenecks, semiconductor engineering has shifted its primary battleground from front-end transistor shrinking to back-end advanced packaging. For decades, chip performance was improved simply by shrinking transistor gates from 14 nanometers down to 3 nanometers. But as physical quantum tunneling limits make further transistor shrinking exponentially expensive, the industry has turned to heterogeneous integration, combining multiple specialized chiplets, power regulators, and memory stacks into a single, tightly integrated 2.5D or 3D package. Advanced packaging allows engineers to integrate power delivery networks directly onto the silicon substrate itself, bypassing inefficient motherboard copper traces and reducing voltage drop across the processor die. However, manufacturing these high-voltage packaging architectures requires hyper-specialized lithography equipment capable of handling thick film deposition, silicon carbide substrates, and ultra-high-purity heat dissipation materials. The companies that design and manufacture these advanced packaging tools, specialized bonding machines, and liquid cooling cold plates have become the ultimate gatekeepers of the technology supply chain. Without their high-precision equipment, advanced chips cannot be assembled, regardless of how many raw silicon wafers are printed at the foundry level. For forward-looking investors, understanding this multi-tiered infrastructure deficit reveals a major structural arbitrage opportunity. While retail investors continue to chase high-flying fabless chip designers, institutional capital is quietly positioning itself in the physical picks and shovels providers that solve the energy density and packaging crisis. First, track the manufacturers of power delivery network PDN components and high-purity silicon carbide. Silicon carbide handles high-voltage power conversion with drastically higher efficiency and lower thermal loss than traditional silicon, making it indispensable for both AI power conversion modules and grid-scale transformers. Second, focus on the specialized back-end lithography and advanced packaging equipment providers. Companies that manufacture the precision bonding equipment required for 3D chiplet stacking and HBM4 assembly hold massive pricing power and multi-year order backlogs that are insulated from consumer tech demand cycles. Third, monitor the lead times of industrial power, infrastructure suppliers, liquid cooling hardware specialists, and high-density electrical component makers. The order lead times for utility, scale power, step-down transformers, and liquid cooling manifolds serve as the primary leading indicator for future semiconductor fab buildouts and data center completions. Following the physical constraints of energy, heat, and packaging is the ultimate roadmap for navigating the next phase of the technology bull market. The returning semiconductor deficit is not a temporary supply chain blip, it is a fundamental structural realignment driven by the immense energy, thermal, and memory density demands of artificial intelligence infrastructure. To summarize our deep dive analysis into 3 actionable principles for your portfolio strategy, look beyond raw silicon. The primary bottleneck in technology hardware has shifted from basic chip design to advanced packaging, silicon photonics, and specialized power management semiconductors. Follow the thermal and energy trail. Companies that solve the data center heat and power grid bottleneck through optical interconnects, silicon carbide power components, and advanced liquid cooling hold unmatched structural pricing power. Monitor infrastructure lead times, track HBM4 yield metrics, packaging equipment backlogs, and utility scale transformer delivery schedules as leading indicators for broader tech earnings and market liquidity. Thank you for tuning in to video 51 of Earnings Per Page. We appreciate every single member of our community who tunes in weekly to skip the noise, save hours of technical research, and retain the financial insights that move the needle. Don't forget to hit the subscribe button. Drop a comment below with your thoughts on the semiconductor shift and keep earning your dividends, one page at a time.